single-phase electrical circuits, the question of whether to count the neutral conductor when derating ampacity is critical. The National Electrical Code, or NEC, mandates that the neutral conductor be considered a current-carrying conductor under certain circumstances. This requirement directly impacts the necessary derating calculations for conductors within a raceway, cable, or enclosure. To fully grasp the necessity of counting the neutral, it's important to define what current carrying actually means. A current carrying conductor is any conductor that continuously carries electrical current under normal operating conditions. This current flow generates heat within the conductor due to its inherent resistance. Excessive heat can degrade the insulation of the conductor, leading to potential short circuits, ground faults, and ultimately, electrical fires. Derating is the process of reducing the allowable ampacity of conductors based on factors such as the number of current-carrying conductors in a raceway, ambient temperature, and other environmental conditions. The goal of derating is to ensure that conductors do not exceed their maximum operating temperature, thereby preventing insulation breakdown and maintaining electrical safety. In a standard single-phase two-wire circuit comprising a hot leg and a neutral, the neutral conductor serves as the return path for the current supplied by the hot leg. Ideally, the current in the neutral is equal to the current in the hot leg, especially when supplying linear loads such as incandescent lighting or resistive heating elements. In these cases, the neutral conductor clearly carries current continuously and must be counted as a current-carrying conductor for derating purposes. However, the NEC provides some exceptions and clarifications regarding when a neutral conductor needs to be counted for derating. The primary exception involves circuits with exclusively nonlinear loads. Nonlinear loads, such as electronic devices with switch-mode power supplies, fluorescent lighting with electronic ballast, and variable frequency drives, generate harmonic currents. These harmonic currents are multiples of the fundamental frequency, which is typically 60 Hz in the United States. The third harmonic, which is 180 Hz, and its multiples, known as triplet harmonics, have a unique property. They are additive in the neutral conductor of a three-phase four-wire system. In a balanced three-phase system, the fundamental frequency currents ideally cancel out in the neutral, resulting in minimal neutral current. However, triplet harmonics do not cancel. Instead, they add up in the neutral conductor. As a result, the neutral conductor can carry significantly higher current than any of the phase conductors, even exceeding the rated capacity of the neutral conductor itself. To address this issue, the NEC requires that in a three-phase four-wire system with nonlinear loads, the neutral conductor must be counted as a current-carrying conductor, and often, it must be oversized to accommodate the increased harmonic current. In single-phase circuits, the situation is somewhat different. While single-phase circuits can also supply nonlinear loads and generate harmonic currents, the additive effect of triplet harmonics in the neutral is not as pronounced as in three-phase systems. However, the NEC still mandates that the neutral conductor be counted as a current-carrying conductor if it carries a significant amount of harmonic current. The threshold for determining what constitutes a significant amount of harmonic current is not precisely defined in the NEC, leaving some room for interpretation and engineering judgment. Generally, if the harmonic current in the neutral exceeds a certain percentage of the fundamental current, typically around 10 to 20%, it should be considered significant, and the neutral should be counted for derating purposes. To accurately assess the harmonic content of the neutral current, it's necessary to use a harmonic analyzer or a power quality meter. These instruments can measure the individual harmonic components of the current waveform, allowing engineers to determine the total harmonic distortion, or THD, of the current. The THD is a measure of the overall distortion of the current waveform due to the presence of harmonics. A high THD indicates a significant amount of harmonic current. When designing electrical systems that supply nonlinear loads, it's crucial to carefully consider the potential for harmonic current generation and its impact on the neutral conductor. Several strategies can be employed to mitigate harmonic currents and reduce the burden on the neutral conductor. Firstly, harmonic filters can be installed at the source of the nonlinear loads. Harmonic filters are designed to block or reduce specific harmonic frequencies, preventing them from propagating throughout the electrical system. Secondly, using phase-shifted transformers can help to cancel out certain harmonic currents. Phase-shifted transformers introduce a phase difference between different sets of windings, which can cause harmonic currents to cancel each other out. Thirdly, specifying equipment with low harmonic distortion can significantly reduce the generation of harmonic currents at the source. Many manufacturers now offer electronic devices with built-in harmonic mitigation features. In addition to addressing harmonic currents, it's also essential to ensure that the neutral conductor is properly sized for the expected load current. The NEC provides specific guidelines for determining the minimum size of neutral conductors based on the load current and the type of load being served. In some cases, the neutral conductor may need to be oversized to accommodate the increased current due to nonlinear loads. When derating conductors in a raceway or cable, it's important to consider all current-carrying conductors, including the neutral, and apply the appropriate derating factors based on the number of conductors and the ambient temperature. The NEC provides tables that specify derating factors for different numbers of conductors. These tables are typically found in Article 310.15 of the NEC. For example, if a raceway contains 4 current-carrying conductors, the allowable ampacity of each conductor must be reduced to 80% of its original value. If the raceway contains more than 9 current-carrying conductors, the allowable ampacity must be reduced even further. It's also important to consider the ambient temperature when derating conductors. The allowable ampacity of a conductor decreases as the ambient temperature increases. The NEC provides correction factors for different ambient temperatures. These correction factors are also typically found in Article 310.15 of the NEC. In addition to the general derating rules, there are also specific requirements for derating neutral conductors in certain types of circuits. For example, in a multi-wire branch circuit, which consists of 2 or more hot legs sharing a common neutral, the neutral conductor must be sized to carry the maximum unbalanced load. The unbalanced load is the difference between the current and the hot legs. If the unbalanced load is significant, the neutral conductor may need to be oversized. Another important consideration is the type of insulation used on the conductors. Different types of insulation have different temperature ratings. The allowable ampacity of a conductor is determined by the temperature rating of its insulation. It's important to select conductors with insulation that is suitable for the operating temperature of the circuit. When installing conductors in a raceway or cable, it's important to ensure that the raceway or cable is properly sized to accommodate all of the conductors. Overcrowding conductors in a raceway or cable can reduce their ability to dissipate heat, leading to overheating and insulation breakdown. The NEC provides guidelines for determining the maximum number of conductors that can be installed in a raceway or cable. These guidelines are typically found in Chapter 9 of the NEC. In summary, understanding the requirements for derating neutral conductors in single-phase circuits is crucial for ensuring electrical safety and preventing equipment damage. The NEC mandates that the neutral conductor be counted as a current-carrying conductor under certain circumstances, particularly when serving nonlinear loads or when carrying a significant amount of harmonic current. To comply with the NEC, it's essential to carefully consider the load characteristics, the harmonic content of the current, and the ambient temperature when designing and installing electrical circuits. By following the derating rules and guidelines provided in the NEC, engineers and electricians can ensure that conductors are properly sized and protected, preventing overheating and maintaining the reliability of electrical systems. Furthermore, proper documentation of derating calculations is essential for future reference and troubleshooting. Detailed records of conductor sizes, ampacity deratings, and relevant NEC code sections should be maintained. This documentation is particularly valuable during maintenance, modifications, and expansions of electrical systems. It aids in identifying potential issues, verifying compliance, and ensuring the ongoing safety and reliability of the installation. Lastly, it is of utmost importance to consult the most recent edition of the NEC and seek guidance from qualified electrical professionals when dealing with complex derating scenarios. Electrical codes and regulations are subject to change, and interpretations may vary. Therefore, staying informed and seeking expert advice is crucial for ensuring compliance and maintaining the highest standards of electrical safety. In conclusion, the practice of derating neutral conductors in single-phase circuits is a critical aspect of electrical engineering and safety. By adhering to the NEC guidelines, accounting for harmonic currents, and considering environmental factors, electrical professionals can design and install robust, reliable, and safe electrical systems. Remember that the neutral conductor in a single-phase circuit should be counted as a current-carrying conductor for derating purposes, especially when nonlinear loads are present or when the harmonic current in the neutral is significant. Always consult the latest edition of the NEC and seek guidance from qualified electrical professionals for specific applications and interpretations. Proper derating practices not only ensure compliance with regulations but also contribute to the long-term performance and safety of electrical installations. By diligently applying these principles, electrical engineers and technicians can play a vital role in safeguarding people and property from electrical hazards. Understanding and implementing appropriate derating techniques for neutral conductors is an essential component of responsible and proficient electrical work.